Naval air power does not begin with targets. It begins with distance. A carrier strike group operates from hundreds of miles offshore, not by preference, but by necessity. A nuclear-powered aircraft carrier is not a stealth platform. Its escorts are not invisible. Once inside a dense, modern air defense environment, survivability drops rapidly. That single constraint shapes everything that follows. In 1991, during Desert Storm, this constraint was already decisive. Iraqi air defenses were concentrated around key urban and industrial nodes, especially Baghdad. The issue was not sophistication, it was saturation. Radar coverage overlapped. Guns overlapped. Missiles overlapped. The probability of detection was not binary, it was cumulative. Every additional sensor, every additional gun, increased the statistical certainty that an aircraft entering the zone would be tracked, engaged, and eventually hit. For the Navy, this created an immediate problem. Carrier-based aircraft were large, fast, and radar-visible. They were designed for fleet defense and deep strike, but not for penetrating a saturated kill box at low altitude. The math was unfavorable. Sending pilots directly into that environment would trade human life for marginal tactical gain. That exchange was unacceptable, not emotionally, but institutionally. The response was not bravery, it was geometry. If aircraft could not safely cross the boundary, weapons would. This is where the Navy's approach diverged from traditional air combat thinking. The focus shifted away from dogfights, maneuver, and pilot skill toward reach, guidance, and launch conditions. The key question was no longer how to defeat the enemy aircraft, but how to affect targets without entering the volume where the enemy's defenses were strongest. This logic reframed the role of the fleet. Ships were no longer just platforms for aircraft, they became launch sanctuaries. Submarines, in particular, offered a unique advantage. They could approach undetected, position precisely, and strike without ever exposing a human operator to enemy fire. The environment below the surface provided what the air above could not: concealment. This was the operating reality that drove early standoff weapons. Not because they were elegant, and not because they were precise, but because they respected the constraint. Distance became a form of armor. The farther the launch point from the defended zone, the more survivable the force. That principle, established quietly in 1991, remains unchanged today, even as the technology has evolved. Understanding this constraint is essential because it explains why the Navy's most consequential decisions were not about aircraft performance or pilot aggression. They were about accepting limits, redefining roles, and designing systems that could function where humans could not safely go. Once distance became the governing variable, the enemy could no longer be defined simply as aircraft or missile systems. The real adversary was density. Desert Storm placed U.S. forces against an air defense environment built on accumulation rather than finesse. Iraqi doctrine emphasized volume. Multiple layers of guns, missiles, and radar systems overlapped, not to guarantee a perfect intercept, but to make survival statistically unlikely. Baghdad in 1991 was not defended by a single system. It was defended by fields of probability. Low altitude was covered by radar-guided anti-aircraft artillery. Medium altitude was dominated by legacy surface-to-air missiles. High altitude was constrained by long-range tracking radars, tied into centralized command nodes. Each layer compensated for the weaknesses of the others. No single system needed to be decisive. Together, they produced inevitability. From a naval aviation perspective, this mattered more than individual platform capability. The A-6 Intruder and the F-14 Tomcat were powerful aircraft, but they were optimized for payload, endurance, and fleet defense. In a dense air defense zone, those strengths became liabilities. Large radar signatures increased detection range. High fuel and payload requirements limited evasive profiles. Speed reduced exposure time, but not enough to meaningfully change the underlying probability. This environment punished penetration. Flying lower increased exposure to gun systems. Flying higher increased exposure to missiles. Maneuvering increased time inside the envelope. There was no altitude, speed, or profile that offered a reliable solution. The kill box was not designed to be impenetrable. It was designed to be unforgiving. The Navy recognized that this was not a tactical failure to be solved with better flying. It was a systemic condition. As long as density remained high, any attempt to insert pilots directly into the defended zone would consume aircraft and crews faster than objectives could be achieved. This realization drove a critical shift in thinking. Suppression and strike could no longer be aircraft-centric. They had to be system-centric. This is where the Navy's role in the joint campaign took shape. While other services focused on penetrating the defenses, the Navy focused on operating around them. Carrier air wings were positioned to apply pressure from the periphery. Submarines and surface ships were tasked with creating effects without crossing the boundary. The goal was not to dominate the airspace, but to reshape it. By treating density as the primary threat, the Navy reframed the problem. Success would not come from defeating every radar or gun. It would come from reducing the system's effectiveness to the point where penetration became feasible for others. This approach accepted that not all parts of the battle needed to be won directly. Some only needed to be weakened. That distinction set the conditions for everything that followed, including the rise of standoff weapons and the increasing reliance on unmanned solutions. From that assessment emerged a requirement that was often misunderstood as a preference. Standoff was not chosen because it was safer or cleaner. It was chosen because, under the conditions of 1991, it was the only approach that scaled. The question was not whether a pilot could survive a single penetration. It was whether the force could sustain repeated operations without unacceptable loss. In engineering terms, standoff defines a boundary condition. It is the minimum distance at which a system can deliver effect while remaining outside the effective reach of the opposing system. In 1991, that boundary was defined by the engagement envelopes of Iraqi surface-to-air missiles. Roughly 50 miles separated survivable airspace from lethal airspace. Crossing that line without first degrading defenses meant accepting losses. This boundary transformed weapon design priorities. Accuracy mattered, but range mattered more. Guidance mattered, but reliability under long flight times mattered more. The weapon had to function independently because the launch platform would not follow it into the defended zone. Once released, the weapon was on its own. This is where traditional air combat logic broke down. Aircraft are adaptable. Pilots can react to unexpected conditions. Standoff weapons cannot. Every uncertainty must be addressed before launch. Terrain, weather, navigation error, and target location all had to be accounted for in advance. The cost of a mistake was not mission failure alone, but wasted sorties and lost time. The Navy accepted this rigidity because the alternative was worse. A pilot is not a replaceable component. Training pipelines measured in decades created an asymmetry between human and machine value. Losing a missile was acceptable. Losing a crew was not. This calculus was not philosophical. It was logistical. Standoff also shifted risk forward in time. Instead of managing danger during the engagement, the Navy had to manage it during planning. Intelligence accuracy became decisive. Mapping quality mattered. Pre-mission assumptions carried more weight because they could not be corrected mid-course. The battlefield extended backward into the planning cell. This explains why early standoff solutions appear crude by modern standards. They were not designed to be flexible. They were designed to be predictable. Predictability reduced uncertainty, and reduced uncertainty preserved lives. By embracing standoff as a requirement, the Navy locked itself into a path, It would prioritize systems that could operate at distance, even if those systems lacked the adaptability of human pilots. That decision would shape naval strike doctrine for decades, and it would expose a new set of limitations that had yet to be resolved. The first practical answer to the standoff requirement was not an aircraft, it was a missile. Specifically, a cruise missile that could navigate without external input once launched. In 1991, that solution was the Tomahawk land attack missile. By modern standards, it was slow, unresponsive, and computationally limited. At the time, it was sufficient because it solved the primary constraint. It crossed the boundary without risking a pilot. The Tomahawk's guidance logic reflected the technology of its era. It did not see the target. It did not receive updates. It followed a pre-planned path using terrain contour matching. By comparing radar altimeter readings to stored elevation maps, the missile could estimate its position over long distances. This allowed it to fly low, remain below most radar coverage, and arrive near its intended aim point without external navigation aids. This approach carried a fundamental trade-off. The missile was autonomous, but not adaptive. It assumed the world would look exactly as planned. If terrain data was inaccurate, error accumulated. If the target moved, the missile did not know. Once launched, the outcome was locked in. From a systems perspective, this limitation was accepted. The targets selected for Tomahawk strikes were fixed infrastructure, command bunkers, power facilities, hardened buildings. These were not expected to relocate during the missile's flight. The weapon was not meant to hunt. It was meant to arrive. Calling the Tomahawk a robot is accurate but incomplete. It was a robot with no perception beyond altitude. Its intelligence was procedural, not situational. It executed instructions faithfully but could not interpret context. This made it reliable in narrow roles and ineffective outside them. The Navy understood these constraints clearly. Tomahawk was never intended to replace aircraft across the spectrum of strike missions. It was a gap filler. It created access by attacking targets that could not shoot back and did not move. In doing so, it reduced the overall density of the air defense system. This reduction was incremental, not decisive. Each missile removed a node, not the network. But over time, these effects accumulated. As sensors went dark and command links were disrupted, the environment slowly shifted. Only then could manned aircraft begin to operate closer to the defended zone. The first generation of standoff weapons solved the immediate problem, but it also revealed a deeper one. A system that cannot see, cannot respond. And as adversaries adapted, that blindness would become increasingly costly. Before standoff weapons could be fully effective, the defensive system they were meant to bypass had to be degraded. This phase is often described as suppression. But suppression is not a single action. It is a system behavior. Its purpose is not only to destroy hardware, but to collapse the enemy's ability to sense, decide, and coordinate. In 1991, Iraqi air defenses relied heavily on radar emissions. Radars searched, tracked, and guided weapons. Those emissions were both a strength and a vulnerability. They provided situational awareness, but they also revealed location. Suppression exploited that trade-off. The Navy contributed to this phase primarily through electronic attack. Aircraft like the EA-6B Prowler did not carry bombs. They carried jammers. Their role was to flood enemy frequencies with electromagnetic noise, reducing radar displays to clutter. This did not destroy the systems, it degraded them. Operators could no longer distinguish targets from interference with confidence. Jamming alone, however, is temporary. Once the noise stops, the radar returns. For suppression to persist, there had to be a penalty for emitting. That penalty came from anti-radiation missiles. When a radar transmitted, it effectively illuminated itself. Weapons like the HARM used that energy as guidance. This created a feedback loop: emit and risk destruction, shut down and lose awareness. Iraqi operators quickly learned this dynamic. The brevity call Magnum signal the missile launch. Hearing it meant that a radar beam was now a liability. The rational response was often to power down. From a systems perspective, this was success. A powered-down radar is functionally equivalent to a destroyed one. It cannot track targets or guide weapons. Suppression achieved its effect without necessarily expending large numbers of missiles. The combined use of jamming and anti-radiation strikes did more than thin defenses. It altered behavior. Operators became cautious. Commanders hesitated. The air defense system lost coherence, not because every component was eliminated, but because coordination became dangerous. This phase demonstrates an important principle. Effective suppression is not about annihilation. It is about inducing uncertainty and forcing the adversary to choose between bad options. By making sensing risky, the Navy and its partners reduced the density of effective defenses without physically removing every system. Only after this degradation could precision strike become feasible. Suppression did not end the threat. It reshaped the environment enough for the next set of systems to operate. Once suppression reduced the immediate threat, a different constraint emerged. Range provided safety, but it also imposed risk. The farther a weapon was launched from its target, the harder it became to guarantee precision. In 1991, this tension was most visible when the Navy was tasked with striking targets that required accuracy beyond what existing standoff systems could reliably deliver. The challenge was not hitting a building. It was hitting a specific part of a building without collapsing the entire structure. Infrastructure targets, such as power generation facilities, demanded controlled damage. The desired effect was functional disruption, not physical destruction. That requirement narrowed the margin for error. At the time, the Navy lacked a purpose-built weapon that combined long range with terminal precision. Closing the distance with aircraft would have increased accuracy, but it would also have reintroduced unacceptable risk. The solution was improvised. Engineers combined components from multiple existing systems to create a hybrid capability. The resulting weapon preserved standoff range while inserting a human into the guidance loop. After launch, the missile transmitted a video feed back to the aircraft. The pilot manually steered the weapon during its terminal phase, adjusting for errors and aiming precisely. This approach worked. It achieved results that fully autonomous systems could not. But it also revealed a cost. To maintain the data link, the launch aircraft had to remain within a certain distance of the target. That requirement kept the pilot exposed for the duration of the engagement. Precision was purchased by accepting delayed risk rather than eliminating it. From a systems perspective, this was a temporary compromise. The human operator provided adaptability that machines lacked, but at the expense of survivability. The loop was accurate, but slow. It depended on human reaction time, cognitive load, and sustained exposure in contested airspace. This phase highlighted a recurring problem. Humans are excellent at judgment and pattern recognition, but they are poor components in high-speed, long-range control loops. The more distance and time involved, the more the human becomes a bottleneck. The Navy learned from this experience. Precision could not depend on keeping pilots tethered to weapons deep into defended zones. The future would require systems that could adapt without continuous human input, preserving both accuracy and standoff. The improvisations of 1991 solved an immediate operational need, but they also made clear that man-in-the-loop control was not a scalable solution. While strike systems were evolving, the fleet still required a shield. That shield was not abstract. It was fighter aircraft tasked with controlling the airspace around naval forces. On paper, the Navy possessed one of the most capable air superiority platforms ever built. In practice, its employment during Desert Storm appeared constrained. The F-14 Tomcat was designed for a specific problem set: long-range fleet defense in open ocean. Its radar, weapons, and endurance were optimized to detect and destroy incoming bombers before they could launch anti-ship missiles. Over land, in congested airspace, those same strengths introduced risk. The central issue was identification. In 1991, identification, friend or foe technology was limited. Radar returns provided range and speed, not intent. Coalition airspace over Iraq was crowded with aircraft from multiple services operating under different tasking cycles. The risk of misidentification was real. The Tomcat's primary weapon, the Phoenix missile, was designed to engage targets at extreme range. In an environment with clean separation, that was an advantage. Over Iraq, it became a liability. A long-range radar-guided missile, launched without positive visual identification, carried the possibility of tracking the wrong aircraft. The consequences of such an error were unacceptable. Rules of engagement reflected this reality. Tomcat crews were required to visually identify targets before firing. This requirement negated much of the aircraft's theoretical advantage. To see the target, the fighter had to close distance, increasing exposure to surface-based defenses. As a result, the F-14 was retasked. Instead of acting as a hunter, it became a sensor platform. Equipped with reconnaissance pods, it penetrated contested airspace to collect imagery and assess damage when satellites were unavailable or delayed. These missions were dangerous, slow, and offered no opportunity for self-initiated engagement. This was not a failure of the aircraft or its crews. It was a manifestation of institutional constraint. Technology had advanced unevenly. Weapon range exceeded identification reliability. When that happens, restraint becomes mandatory. The Tomcat's experience illustrates a broader principle. Capability alone does not determine use. Systems are governed by the weakest link in the chain. In 1991, that link was identification and coordination, not firepower. After the retirement of the F-14, the Navy faced a measurable gap. Air superiority could be maintained locally, but long-range control of airspace degraded. The F/A-18 Hornet family was flexible and reliable, but its reach was limited. Range was no longer defined only by fuel or pilot endurance. It was defined by weapon kinematics. Restoring that reach did not require a new fighter. It required a different use of physics. The key insight was simple. Where a missile starts matters as much as how it flies. A missile launched from sea level begins at a disadvantage. Dense air, zero forward velocity, and gravity all impose an energy cost before the weapon can even begin its mission. Launching from an aircraft changes those conditions. At altitude, the air is thinner, drag is reduced. Released at high subsonic speed, the missile inherits kinetic energy it did not have to generate. Fuel that would have been spent climbing can now be spent accelerating and maneuvering. This logic led to the adaptation of existing surface-launched missiles for air launch. By carrying a large missile on a fighter, the aircraft effectively becomes the first stage of the weapon. The result is not incremental improvement. It is a step change in range. From a systems perspective, this approach is efficient. It leverages existing inventories and proven propulsion systems. It avoids the cost and time associated with designing a new missile from scratch. The trade-off is integration complexity. Aircraft must be modified to carry heavier loads. Flight envelopes change. Tactics must adapt. The increase in range alters the geometry of engagement. A fighter no longer needs to approach the defended zone to influence it. It can remain outside the threat envelope while still contributing to air and missile defense. This restores a degree of standoff that had been lost. However, range alone does not solve the problem. A missile with extended reach still requires targeting data. Without accurate, timely information, range becomes theoretical. The platform that launches the weapon does not have to see the target, but the system does. This sets the stage for the next shift. The decisive factor is no longer the missile or the aircraft. It is the network that connects sensors, shooters, and decision-makers into a single operational picture. By the mid-2000s, the center of gravity had fully shifted away from individual platforms. The limiting factor was no longer range or payload, it was information flow. A weapon's effectiveness now depended less on what it carried and more on what it knew, and when it knew it. In 1991, the combat network was human. Early warning aircraft detected contacts. Controllers interpreted radar returns. Information moved by voice over radio. Every step introduced delay, ambiguity, and loss of precision. The system functioned, but it operated at human speed. Modern naval warfare replaced that structure with data-centric integration. Sensors no longer exist to serve their host platform. They exist to feed the network. A radar track, an infrared signature, or an electronic emission becomes a shared object, available to any node authorized to act on it. This changes roles fundamentally. A stealth aircraft operating deep inside contested airspace does not need to fire its weapons to be decisive. It can remain passive, collecting data without emitting. That data can be transmitted to other platforms operating hundreds of miles away, including ships that never come within visual or radar contact of the target. The shooter, in this model, may never see what it destroys. A surface combatant can launch a missile based entirely on remote sensing. The missile itself may receive updates in flight from a platform it has no direct relationship with. Guidance becomes distributed. Responsibility becomes collective. From a systems standpoint, this reduces exposure but increases dependence. The effectiveness of any single action is tied to network integrity. Jamming, cyber attack, or data corruption can degrade the entire system without destroying a single platform. Survivability shifts from armor and maneuver to redundancy and resilience. This is the trade-off. The network enables reach and precision at unprecedented scale, but it also creates a shared vulnerability. The Navy accepts this risk because the alternative is worse. Operating as isolated platforms in a dense, contested environment would rapidly exhaust both machines and people. In this architecture, the human role changes again. Pilots and commanders are no longer primary sensors or shooters. They become managers of information flow. Decisions are still human, but execution is increasingly delegated to machines operating at machine speed. The network did not make warfare simpler. It made it faster, more interconnected, and less forgiving of error. Understanding that shift is essential because it explains why modern naval power is measured less by hull count or aircraft numbers and more by the quality of its data links. Looking back at Desert Storm, with the benefit of 3 decades of development, its significance is often misunderstood. The campaign did not prove that mass no longer mattered, or that technology alone guaranteed victory. What it demonstrated was a structural transition in how military power is applied under constraint. The final operations of the battleships Missouri and Wisconsin are instructive. Their guns delivered enormous kinetic energy. They were reliable, survivable, and psychologically imposing. Yet their effects were limited by range, accuracy, and response time. They could influence a coastline, but not the deeper system supporting the enemy's ability to fight. In contrast, relatively small numbers of precision-guided weapons produced disproportionate effects. They disabled power, command, and communication nodes without requiring sustained presence over the target. This was not efficiency for its own sake. It was a response to the environment. Dense defenses punished exposure. Precision reduced the need for it. From an engineering perspective, this marked the decline of what could be called brute force solutions. Adding armor, adding firepower, or adding numbers did not scale against increasingly capable sensing and targeting systems. However, this transition did not eliminate uncertainty. Precision weapons depended on accurate intelligence, functioning networks, and predictable target behavior. When any of those assumptions failed, effectiveness dropped sharply. Desert Storm succeeded in part because the adversary's ability to disrupt those enablers was limited. The lesson, therefore, is conditional. Precision and standoff work best when supported by information dominance. They are not universally decisive. Against a peer adversary capable of contesting sensors and networks, the same approaches face significant friction. What Desert Storm ultimately validated was not a specific weapon or platform, but a design philosophy. Protect humans by pushing machines forward. Use distance to manage risk. Accept that no system operates in isolation. That philosophy continues to guide naval development, but it does not resolve every problem. There remain situations where distance collapses, information degrades, and systems fail. Those cases define the limits of the model, not its success. The unresolved tension appears when distance can no longer be maintained. Standoff assumes space to maneuver, time to plan, and networks that remain intact. In practice, none of those conditions are guaranteed. Adversaries adapt. They move targets, compress timelines, and deliberately attack the systems that enable long-range control. This is where the limits of automation and networking become visible. Robots extend reach, but they still rely on assumptions about connectivity and sensor availability. When links are degraded or denied, autonomy fills some gaps, but not all. There are decisions that still require judgment under ambiguity, and those decisions cannot always be pre-programmed. As a result, naval doctrine did not abandon manned aviation. It redefined its purpose. Aircraft were no longer optimized solely for a single mission, such as air superiority or strike. They were required to switch roles dynamically, carrying sensors, weapons, and electronic effects in the same sortie. Flexibility became a survival trait. This shift led to the concept of the integrated strike package. Instead of sequential phases executed by specialized platforms, multiple functions are combined and executed simultaneously. Detection, suppression, strike, and defense occur in parallel, not in sequence. This reduces reliance on perfect conditions and shortens the window in which the adversary can react. The implication is important. When distance collapses, success depends less on individual performance and more on coordination under pressure. Multitasking is no longer a convenience. It is a requirement imposed by contested environments. Desert Storm established the blueprint for operating at range. What followed was the recognition that range alone is insufficient. Systems must be designed to transition smoothly from standoff to penetration without collapsing. That transition zone is where risk concentrates, and where human judgment remains most critical. This is not a return to pilot-centric warfare. It is an acknowledgement that even the most advanced systems have edges where automation degrades. At those edges, trained humans absorb uncertainty on behalf of the system. That is the handoff point. The long reach and the shield create the conditions for action, but they do not eliminate the need to operate inside the threat envelope. Understanding how the Navy manages that transition is the next step in decoding modern naval warfare.